Okay, so thank you to David and Jane. So I'm going to give I'm sort of going to give a short talk, an introduction to the CI's climate models. I want to say a few remarks first. So you'll see that there's a lot of discussion period programmed into today. Okay, so the idea is that three esteemed people from the community, that's not me, okay, give talks, hopefully to stimulate ideas, followed by discussions and questions and answers in those discussions. So I want you to feel able to ask questions, however daft you think they might be. Okay? There's almost no such thing as a stupid question. Okay? So I've recently painted my room at home. I don't like the colour of the room. It's awful. So pewter green, you could have thought. So what's the best way to get rid of the paint? Okay? Well, quick and easy, burn it off. Yeah? Can anyone see a problem with that idea? Okay? So there's no such thing as a stupid idea, right? Okay? Well, that may seem like a stupid idea, but apparently this was one of the ideas which stimulated the formation of paint stripper. Okay? Which is not a stupid thing. People do use paint stripper. Okay? So I may have made that anecdote up, but I thought I read it somewhere. But it illustrates my point that ideas, no matter how daft they may seem, inevitably lead to channels of thought which can be useful. Okay? With that point that there are no stupid questions or talks, I'd like to introduce my talk. So I'm hoping there's nothing controversial in this talk. This is really just to set the scene, okay? So it's going to be a 20-minute trot through sea ice, what it is, why it's important, and some ideas of how to model it. Now, if you've been studying sea ice for many years, you're not going to learn anything, okay? But it will hopefully warm you up for the rest of the day. And I know that several people in the audience, like students who haven't had 10 years working on sea ice for some reason, okay, may actually learn something from this. So, introduction to sea ice climate models. So here's the talk structure as advertised, what it is, why it's important, how is it changing, some brief high-level ideas of how we actually model sea ice and climate models, some reflections. I'm just going to be fairly light on that because I suspect this is going to form the meat of today's discussions, and then some summary remarks. Okay, so what is sea ice? Sea ice is frozen seawater. It floats as a layer on the ocean. It's a layer that's a few meters thick, sits between the air above and the ocean below, acts as a partial barrier to transfers of heat, moisture, and momentum. Okay? Covers a large fraction of the ocean's surface, and of course it waxes and wanes seasonally, as we know. Now, this is embarrassing to state this, so I'm going to state it anyway. Sea ice is not an iceberg, okay? It's amazing how many times I have to make this point, okay? Icebergs are not sea ice. Icebergs have very different aspect ratios, their methods of formation are very different, okay? Today's discussion is about sea ice. So sea ice comprises floes, which are wide, thin plates, this sort of dimensions, 100 meters to 10 kilometers, 10 centimeters to 5 meters thick or so. So these wide, thin plates, which in the summer are kind of separated. In the winter, they can freeze together to form larger flow aggregates. Here you can see what happens when flows bump into each other, break up into blocks to form pressure ridges. Also, you can see these leads here, which are long, thin features in the ice cover, normally due to mechanical divergence. So why do we care about sea ice? This is from a climate perspective. So, of course, the number one reason, or at least the reason that springs to my mind first, is that it has a high albedo, high reflectivity, and so this strong difference in albedo between the ice and the snow and the open ocean is what strengthens the albedo feedback mechanism. And so that has been attributed as one of the main causes for the enhanced surface warming in the polar regions. And some models show it up to 5 times greater in the polar regions. Of course, when seawater freezes to form sea ice, the sea ice is less saline than the water from which it formed. Okay, so that means salt is released into the ocean, and that densifies the water and drives or plays a leading role in driving these thermohaline circulations of the ocean around the world. Particularly in the Southern Ocean, we have lots of dense water formation in the Weddell Sea, and I think that's been the activity of basically there's a research group in the Bass, which is down the road, has been studying this for, I don't know, as long as I've been alive, it seems like, for a long time. So I mentioned sea ice is between the air and the ocean. It dramatically insulates the air from the ocean. Okay, so in winter the heat flux is just like a few watts per square meter through the ice, whereas when you have a break in the ice cover, the heat flux goes up to hundreds of watts per square meter. So it has a dramatic impact on moderating that heat flux. So also the timing of when sea ice is there affects the timing of heat transfer between the air and the ocean. So that has a big impact on storms. So this also has an impact on us at lower latitudes potentially. So here are some physical reasons why someone who doesn't live in the polar regions would care about sea ice. But also it is an important part of the climate. People actually do live around sea ice, and creatures live on sea ice. So knowing about sea ice is important for people's way of life, and of course polar bears, and we all love polar bears, right? So it's a quick rattling through what sea ice is and why it's important. What I didn't mention is that it's also arguably the canary down the mine shaft. Okay, if we consider there to be climate change, it looks as though sea ice is a sensitive indicator of that climate change. I suspect we're going to hear quite a lot about plots like this. So I just point out that the Arctic sea ice summer extent has been decreasing quite dramatically. South versus north. So this is from a paper by Ian Eisenman, who was here a couple of weeks ago. So these are CMIP model outputs. I think the dark blue is the mean, I guess, and this is the standard deviation around it. This is the Arctic and Antarctic summer and winter. So what you can see is that the Arctic sea ice extent has been reducing rather dramatically, arguably more dramatically than one would expect from climate model projections. Until really quite recently, like last year, okay, there has been this small increase in Southern Ocean sea ice. You can argue about whether that's statistically significant or not, but what it isn't is decreasing. Okay, so it's interesting that the climate model projections don't appear to be capturing the strength of the Arctic ice loss and even the sign of the Southern Ocean sea ice loss. Having made those comments, there's a strong argument about the importance of natural variability, which I suspect is going to be the content of the next talk. That's just sea ice extent. This is Arctic sea ice volume. So this is the black dots show the mean seasonal cycle from 79 to 2016, so that's a satellite data era, from PIOMAS. So PIOMAS is an ice ocean model that data assimilates sea ice concentration, doesn't assimilate thickness. But nonetheless, this is probably our best way of assessing how the volume has been changing. So particularly you can see the last 7 years down here, all below the one standard deviation from the mean. Okay, so you can see the red line is this year. Okay, so you see the sea ice volume has been lost in the Arctic as well as the extent. Okay, so that's what's happening to the sea ice cover. Now a bit about modelling sea ice and climate models. Sea ice models are formulated as continuum expressions of local balances of momentum, mass and heat. So that's pretty much a similar sort of thing to any climate model component, the atmosphere or the ocean for that matter. Within a certain grid cell of a climate model, you've got a whole bunch of things going on. Okay? So you've got melt ponds, bottom melt, you have redistribution of ice and ridging, you have new ice formation, frazzle ice being formed here, you've got percolation of water through the ice when it's porous, you've got brine drainage, okay? Got loads of things going on, and all of these are within a grid cell. So you're not resolving these things, okay? You have to parameterize them. So I'm just going to quickly touch on the headline balances, momentum, mass, and heat. Here is the local momentum balance of sea ice that appears in client models. This is a vertically integrated horizontal momentum balance. So as I say to my students, this is F equals ma. Okay? Mass times acceleration equals the balance of forces. So air drag, ocean drag, ice interaction forces are the dominant players here. Okay, this is the magnitudes here. So Coriolis is tiny, the sea surface tilt is tiny, the inertia is very tiny. Okay, so in particular, we know because the inertia is very tiny, we don't have turbulent sea ice. Okay, there's no such thing as turbulent sea ice. The wind may blow the ice around in lots of little interesting meanders and squiggles, but the ice itself is not turbulent. Okay, so that's the momentum balance. That's what the deformation looks like. So, as a mathematician, I naturally think that's smooth and continuously differentiable, and think, oh, I know what, I'll use the Navier-Stokes equations for that. Well, actually, that's what people did do when people first started modelling sea ice, until they actually looked at it and saw that the deformation was discontinuous, sudden. It occurs as though a critical criteria has been met. So the rheology of sea ice is not modelled like a Newtonian fluid at all. It's actually modelled as what's called a plastic material. So I guess the main feature of plastic material is once the stresses reach a certain critical value, it irreversibly deforms. And in the case of sea ice, that is largely through cracking or flowing or flows flowing past each other or pressure ridges forming. So the critical stress in stress space with two horizontal deformation takes this sort of shape. Okay, so this is the famous stroke infamous elliptical yield curve introduced by Bill Hibbeler. So this is still used in most client models, probably all client models. Okay, work is happening on that, but it does capture the main features of plastic deformation and the ratios of the stresses to cause that deformation. Okay, that's the momentum balance. Now there's the thickness balance for sea ice. So until really very recently, and I believe this is still true in all client models, the state variable for sea ice is the thickness distribution. Okay, so the ice is characterized by the area abundance of different thicknesses. So this is the evolution of the thickness distribution. That's an example plot of the thickness distribution versus thickness distribution. This is evolution in time due to melting and freezing, mechanical divergence of the ice cover, and mechanical redistribution of ice. So this is this process here, psi, mechanical redistribution of ice, is what transforms thin ice into thick ice. This is pressure ridging. So this is again a smoothly continuous differentiable function, etc. But nonetheless, in client models, that's basically 5 thickness classes. You can increase that if you like. Some of my work has increased it. But in client models, at least good client models, it's 5 thickness classes. Some models, it's 1 thickness class. Okay, you've got open ocean ice. So that mechanical redistributor, psi, is poorly understood and known. This is an example of discrete element model simulation to try to simulate the redistribution of ice, and from that learn what functional form it should take in client models. Okay? But there's still uncertainties in this, and I think there were quite a few talks on this a couple of weeks ago at the workshop on multi-scale sea ice. So that's momentum balance and thickness. Now let's talk about heat and salt. Okay, so this is the conservation of salt inside sea ice, conservation of heat inside sea ice, And because the dendrites are very small and diffusion is relatively rapid on those small length scales, the heat and salt lie on the equilibrium phase diagram for sea ice. So I've called this a mushy layer because that's the generic term, where various representations of these basic balances have appeared in sea ice before, called different names. Go back to Make and Unstein in 1971, a classic thermodynamic sea ice model actually is a mushy layer model. They wouldn't have known that, they wouldn't have called it that, they might have resented it being called that, okay? But it was a mushy layer model. So key point here is that the internal solid fraction is varying. So the ice is not an impermeable, boring slab of ice. Okay, it becomes permeable in the summer. This has huge impacts for salt transports and also biogeochemistry. Oh, quite know how that got in there. So apparently melt ponds are important. Who have guessed it? Okay, so an example of something that affects the heat and mass balance is the presence of melt ponds on the surface. So this is an example of a process which is parameterized in various ways at various levels of sophistication inside client models. Now, it's not quite true to say that melt ponds have not been represented in client models before because they have had albedos that have been function of surface temperature. But until relatively recently, it wasn't the case that ponds were explicitly modelled themselves. There was no mass balance for surface meltwater. And I think we can thank Elizabeth Hunke for getting the sums right on that, actually, because once we developed the model, getting it to actually function to our client model is non-trivial. Okay, so that's a quick rattle through modelling of sea ice. So hopefully those of you who have a sort of a mathematical background in continuum mechanics can quickly get up to speed of what we're interested in. So what do I have? A few minutes, right, good. So I just want to say a few words about what these sea ice models are used for. So today's talk is obviously primarily about climate sea ice modelling, but actually these models are used for various different reasons. Okay? And I'm not listing all the reasons, the way they're being used here. I want to highlight a few. In particular, ice weather prediction. So the Navy and industry who want to navigate across the Arctic care about where the ice is at any one time, how thick it is. Okay? So there are such things as ice weather predictions. So these are sea ice models. You want to run at high resolution. You want to know where the ice is, where my ship is. Okay, so if your ship is less than 200 kilometers, you need a model that resolves that. Okay, so high resolutions are needed. You typically run in this model for a short period of time, days, maybe a week. Okay, typically days. So the initial conditions are crucial. Okay, you can't spin up from open ocean. Where the ice is important. And also, you have the possibility of data assimilation. You actually know where the ice is. You have satellite imagery. So these are examples of the models which you run forward in time over short periods at high resolution. Initial conditions are hugely important, and typically you'll be using data assimilation of some kind. So I just point out in passing that when you use such high resolutions, you may be invalidating the continuum assumption, which is underlying the initial structure of these client models. Okay? The assumption is that a grid cell contains a representative sample of sea ice, but if your grid cell is 500 meters across and you only have half a flow in that grid cell, that is not a representative sample of sea ice, that is the flow. Hindcasts. So this is where you run a sea ice ocean model, force it with atmospheric reanalysis, and you do this for the past, obviously, because you've got the atmospheric reanalysis. And the idea is to try to work out why the ocean or the ice changed and to understand what caused it to change and therefore get some insight into the process. A good example of this is, another reason for doing this is to fill in data holes. So a good example of this is biomass, where you're running a model forced reanalysis. In this case, you're using data assimilation of ice concentration, okay? And you get possibly our most accurate state estimate of what the ice cover is. And also you get to really test your model because you are really trying to compare your model on a certain day with data from a certain day. So it's a stringent test of simulations. So these are two reasons why we need sea ice models, sea ice client models. And of course, there's also client models. Okay? You use sea ice client models for climate modeling. So I'll focus on this one. So here, some obvious comments which are worth stating nonetheless. Okay, initial. Oops, amazing. Right, yeah. Okay. So some obvious comments worth stating. Initial conditions are irrelevant. Okay, data assimilation isn't possible. If you're doing a climate projection 100 years in the future, you don't have any data to assimilate, right? If you're doing a climate projection 100 years in the future, so what about the initial conditions? It will have changed. When you do a climate model prediction, okay, you are typically using a model which has got a relatively low resolution, although what was low resolution 20 years ago when I started getting involved in sea ice is, no, sorry, let me explain where. Yeah, what was a high resolution 20 years ago now becomes like a low resolution today. I imagine we'll hear something about that later on. This other point which is worth making, which is blindingly obvious to anyone who works in climate modelling, but maybe not so for those who don't, is that climate models, they're predicting, you tend to run a climate model many, many times, get an ensemble of projections, and then you just try to understand the statistics of the projections. You're not trying to map a particular climate projection against a particular sea ice cover at a particular time. So when we run a climate model and we say, oh, well, it doesn't look like the present day, well, that's not surprising. Okay? The atmosphere in the model is different. The ocean is different. Why should it look like the present day? So that's part of the role of natural variability. So just to summarize those things then, so sea ice is an important component of the climate system, a sensitive indicator of climate change. We've seen rapid changes in the Arctic. They're based on continuum local balances, momentum, mass and heat. Sea ice generally behaves as a plastic material and it's a mushy layer. Climate models have some success in simulating the range of sea ice extents, but also have some problems with simulating the sea ice state, its thickness, its motion, etc. Why? Could be all sorts of reasons. Natural variability is an important part. Chaos, I imagine Dirk will talk about that next. Okay. Naturally, there are problems in the atmosphere and the ocean, because those are the bits I don't work on. Okay. But also, there are problems in the sea ice as well. So hopefully today we will learn more about how and why sea ice models are worth having, how they can be useful, and maybe how to improve them. Thanks very much.